Well, guys, today we are going to study about Bernoulli's principle. It is named after Daniel Bernoulli. He actually stated a relation between pressure head, velocity head, and datum head. What is datum? It is actually the elevation head. It is as simple as that. Actually, you can express in other terms also pressure energy plus kinetic energy plus the potential energy. uh, this is your pressure energy PR, suppose this is kinetic energy Ke, and this is a potential energy is equals to constant. Okay, and suppose I'm taking this term, kinetic energy, it is what? It is half mv square. If I divide it with mg, suppose kinetic velocity per unit weight, this is weight, kinetic velocity half mv square per unit weight divided by mg, so it cancels off. I'm getting v square by 2g. And what is its unit? Its unit is actually meters. That's why it is termed as velocity head. Similar is the case of datum head, and this is the case of pressure head. He says that for a steady flow, in a single streamline, all the points which are lying on that streamline have the summation of pressure energy, velocity energy, and the potential energy constant. Suppose if you consider that this is your streamlines, okay, suppose you have in this streamline you have got 1 point, 2 point, 3 point. In this point, this is p1, this is p2, this is p3, this is point number 1, 2 and 3. If you find the summation of the potential energy, kinetic energy, and the pressure energy, and summation of these energies over here, and these summation of these energies over here, you will find that all these summation of the energies are constant in a single streamline. Similarly, in this streamline also, the summation of energies for different points are constant. Now, if you don't have the concept of steady flow, no problem, I'm going to discuss over here. See, this is the figure. Suppose this is a pipe, okay, pipe of any type, any cross section. Suppose I'm considering a point P. Suppose fluid, there is fluid, okay, liquid is flowing through this pipe. Suppose I'm seeing the velocity at point 1 at 10 a.m. in the morning. I am finding that the velocity is 10 meters per second. I will observe that at 7 p.m. in the evening also the velocity is 10 meters per second in this point P. Okay, so we can see that in case of a steady flow at a particular point, it may be this point or maybe this point, any point at a particular point, the fluid parameters, for example velocity, pressure, it does not changes with respect to time. Okay, so dv by dt equals to 0. You can also say dp by dt equals to 0. All the fluid parameters do not alter with time. Now suppose we are going to see that how we can apply the Bernoulli's principle in case of different kinds of pipes which are at different elevations, pipes of same cross section, different cross section, everything. Okay, suppose this is a horizontal pipe, this is a pipe, okay, this is a horizontal pipe, and this line shows the center of the pipe. Okay, now I will apply Bernoulli's principle in point 1 and point 2 of the pipe. So according to Bernoulli's principle, P1 by rho g plus V1 square by 2g plus Z1 must be equals to P2 by rho g V2 square by 2g plus Z2. What is P1 by rho g? Pressure head at point 1. V1 square by 2g is the velocity head at point 1. Z1 is the datum head. at point 1. What is Z1? It is the height. It is the height from the base level. What is the term datum means? Datum means base or zero level. Okay. If I have to take the height, if I consider this as my zero level, then the height of the center of the pipe is Z1. Height of the center of the pipe here is Z2. So Z1 and Z2 are equal. So Z1 cancels off Z2. Since the area of the cross section at point 1 and at point 2 is same, the area does not changes. So by continuity equation we can see that A1 V1 equals to A2 V2. So V1 must be equals to V2. Okay, so this is V1 square by 2g cancels off with V2 square by 2g. Now I'm left with what? P1 by rho g and P2 by rho g. So I get this thing that P1 by rho g equals to P2 by rho g. So the pressure head at 1 and 2 is equal. Okay, we know that if the velocity increases, area goes down. Velocity increases, area goes down. We have seen it in practical life also, that if we hold the nozzle of the pipe, if we just press this, suppose this was the nozzle of the pipe, if we press the nozzle, area of cross section gets decreases, so the velocity will increase. That is the case here. Area is same, so velocity cancels off. So I'm getting this thing. Now if we apply Bernoulli's principle in case of pipe like this, okay, suppose this is my pipe, this is the inlet of the pipe, and this is the outlet. If I apply Bernoulli's principle at the inlet, I'm naming the inlet as 1.1, and this is the outlet, I'm naming as 0.2. Okay, I can see that the outlet is at the height Z2 from the datum. I've considered datum now as the center of the pipe. Okay, then the height at the inlet will be 0 because this is the datum. There is no height. Here is the height. Okay, Z2. So writing the Bernoulli's equation, now I can see that Z1 equals to 0 because there is no height. If I consider this as a datum, there is no elevation of the datum from the center of the pipe. So so we have got value of Z2. Of course it is not 0, but try to understand that the cross sectional area, this is the cross sectional area does not changes. Here the cross sectional area at 1 is equal to the cross sectional area at 2. So V1 square by 2g is actually equals to the V2 square by 2g. So both cancels off. So I'm getting what? P1 by rho g equals to P2 by rho g plus Z2. Okay, so definitely I'm getting that P1 is greater than P2. Okay, actually this is Bernoulli's principle. Here you have seen that your elevation here in this problem, especially elevation is 0. That means what? Elevation has gone down in this side. So to balance the equation, your pressure must be higher. So the pressure must be higher. This is the Bernoulli's equation, that it is actually based on the conservation of energy. If your potential energy goes down, pressure energy has to go up to balance this. Okay, so you can get here that P1 is of course greater than P2 because you have to add Z2 with P2 to make it equals. Okay, now we are seeing this type of pipe. Suppose if my pipe is this, water is flowing through this pipe, and I'll show that if what will happen if I apply Bernoulli's principle at point 1 and point 2. See, this is point 1 So writing the Bernoulli's equation, now this is the center of the pipe. If I take my this as the datum, or you may take their center also as the datum, so you can see that the elevation of point 1 and the point 2 from this level is actually same, so z1 cancels off with z2. Now here the area of cross section at 1 and area of cross section at 2 is not same. Cross sectional area at 1 is more, so you can understand that here velocity will be less and here velocity will be more. This we can understand from our common concept. So of course v2 will be more than v1, so this cancels off. Suppose I'm giving it a value, v1 is 10 meters per second and v2 is 20 meters per second. If I put these values, it is 10 square by 2g, it is 20 square by 2g. So from the equation I can see that P1 is higher than P2. This is Bernoulli's equation. If velocity goes down, if velocity decreases, then pressure at this point needs to be go higher to balance the equation. Here if the velocity increases, if you want to balance it, pressure must go down. That is what I have seen, that P2 is less than P1. So have you understood Bernoulli's principle now? It is fantastic. Once you start understanding Bernoulli's principle, your concept in fluid mechanics will get better and better. Now Bernoulli's equation can be applied in a Venturi meter. What is Venturi meter? It is a device which measures the discharge. What is discharge? It is V dot. V dot. What is V dot? It is volume by time. It is the rate of it is the amount of volume of water coming out from the pipe in per unit time. Okay, so the Venturi meter is this device. You can see I'm bordering. Okay, this is my Venturi meter. Its shape is somewhat like this. It is constricted at the middle. Okay, it is constricted at the middle. This constricted portion is known as throat. This is the inlet. This is the inlet portion and this is the outlet portion. Suppose water is entering through the pipe. Now I have used a U-tube manometer. Probably you must already know about the U-tube manometer, concept of U-tube manometer. If you don't know, no problem. In this, while I'm going to explain you. See, let me first apply. I'm going to tell you about this reading of the U-tube manometer, but beforehand, see here. If I apply the Bernoulli's equation in point 1 and point 2, okay, so what will I get? This is P1 by rho g plus V1 square by 2g plus Z1 equals to this thing. Now you can see that the elevation, if I see this is the center of the pipe, if you call this level as your datum or you assume this as your datum. If you assume this as your datum, then Z1 is 0, Z2 is 0. If you assume this as your datum, then the height from this point to this point and this point to this point is same, so Z1 cancels off with Z2. So the matter is same whichever point you considered as datum. Now suppose P1 by rho g plus V1 square by 2g is equals to P2 by rho g plus V2 square by 2g. Z1 Z2 cancels off. So I can bring my P2 over here. P1 by rho g minus P2 by rho g equals to V2 minus V1 square by 2g. Okay, I can write this. There is no harm. Actually this is like this. Okay, Now this, I know this is the pressure head. See, this is your P1 by rho g is the pressure head at inlet. Similarly, P2 by rho g is the pressure head at outlet. This is the pressure head. This is the pressure head at outlet. P2 by rho g. So what is the difference between the inlet and the outlet pressure head? Is the differential pressure head. The difference, it is H. H is also equals to this thing. Okay. Now see, try to understand. We have seen that the mercury level, suppose the fluid inside the U-tube manometer is mercury. We have seen that the mercury level has risen up from this side. That means what? Here the pressure is more. The suppose here the fluid is water. Water has pushed the mercury. Now you can see it, I think. So here the pressure is more. Okay. So the water has pushed the mercury and the mercury has risen from here. Okay. If you consider the case like this, suppose this is my U-tube. Okay, this was the initial level of mercury. Okay, when the pressure at both the sides are same. Okay, this is the initial level of mercury. But when the pressures, this is 1 point, this is 2 point, when the pressure at both the sides of the U-tube manometer at 1 and 2 are same, I am seeing that the mercury level is absolutely like this. But when the pressure at 1 increases, the fluid actually forces, the fluid flowing through the Venturi meter forces, its pressure is high, so it forces the here, it gives its pressure or force over here, so the manometric fluid, that is the mercury, it rises. So the new level of the mercury is here, this is over here and it rises over there. Okay, if it moves a distance of, the distance moved here is equals to distance moved here, and we call this distance as x. This is the reading of the mercury. So the final liquid level is the portion which I am darkening. Have you got it? So this, so the manometer actually shows that the pressure at point 1 is higher than the pressure at 2, and you can find out by this, by Bernoulli's principle also. See, I know that area at 2 is very less, so the velocity at 2 will be higher. Okay, and area at 1 is large, so velocity will be low compared to V2. V1 will be low, V2 will be high. So if V2 will get high, then P2 must become low to balance the equation, and P1 must become high. And that is what your mercury has shown. Your mercury has shown that exactly. Okay, now you get the concept of Bernoulli's equation. Actually, apart from pipes and all, Bernoulli's equation has also a great application in the field of aerodynamics, like the wings of the aeroplanes, how the wings of the aeroplanes should be made. In this video, actually, I'm showing you a little bit portion. It is a different chapter, but still, so that you get interest in reading this Bernoulli's equation, I'm showing you. Okay, so see, wings of the aeroplane is somewhat like this. Somewhat it is of this shape. Okay, you see the submarines also of this shape. Okay, why? What is the function of this shape? See, actually, when the air is flowing like this, it goes from here and then it comes down and it goes over there. Okay, so here the velocity is low and here the velocity is high. Okay, so low velocity means high pressure. From Bernoulli's equation we have seen that if velocity goes down, you can see here that if velocity goes down, pressure goes up. That is the case here. When the air is flowing underneath the wings, below the wings, the velocity is low. Okay, and here the velocity is high. So here the pressure is low. So the pressure is low. So here underneath the wings it is high pressure, above the wings it is low pressure. So the wings actually gets a lift force, high pressure. The air at the below is under high pressure, so it pushes the air at upwards. This is low pressure. It tries to move from high pressure to low pressure. Okay, we know that water also tends to flow from high pressure to low pressure. Similar is the case with air. So the aeroplane gets an upward lift. That's why aeroplane can rise. So okay, so this is a different concept actually. If you have interest, you can actually see the modeling of aerodynamics. Cars are also modeled in this way, but the basic concept lying behind all this is the Bernoulli's principle. I hope you have get the concept, and if you have any doubt you can comment on the video, and if you have liked it please subscribe. Thank you.